All right, so we're talking about section 5.4 in this video, which is greatest common factor and least common multiple. These are terms that you are most likely already familiar with. We introduced these all the way back in pre-algebra, actually, and arithmetic. They're really important concepts. Greatest common factors play into how you simplify fractions and things like that, and they're useful in a lot of word problems, a lot of applications, stuff like that. So let's start with some definitions. If you have two natural numbers, a and b, then the greatest common factor, which we also frequently call the GCF, or in most higher level literature, we actually don't call it that. Typically, we call it the greatest common divisor, which is GCD. Either of those are the same term; they mean the same thing. The GCF or the GCD of A and B is the largest factor that both numbers have in common. Okay, and oftentimes you'll see me using this notation throughout the notes here, even though your book doesn't really use this notation that I can remember. GCD with the parentheses A, B means the greatest common divisor of those two numbers. So we use this notation to denote the GCD or the GCF a lot. Now, if you want to find the greatest common factor of two natural numbers, we're going to talk about how to do that. But you can also talk about the greatest common factor or greatest common divisor of any collection of natural numbers, two or more natural numbers. So if I have this whole list here, M1, M2, all the way through Mn, I can find the greatest common divisor of all of those by looking for the largest factor that all of these have in common. And I can write that this way. Okay, so for us in these notes, the largest set of numbers that we'll find the GCF or the GCD for is three numbers, and you see I have an example like that right here. Now there's several different ways of determining what the greatest common divisor, the greatest common factor of two numbers are. One thing I could do, for example, I want to find the greatest common divisor of 36 and 48 in this example. I could write all of the factors of 36, which we've shown how to do that, and I could write all of the factors of 48. That creates two lists of factors, and then I just search for the largest factor that shows up in both lists. That's one way to do it. The problem with that approach is that oftentimes the numbers that we're dealing with may have a lot of factors, and so that can take a long time searching for all of those. Also, if we're taking the GCD of several numbers, that's a lot of lists that you have to come up with. So there is a better way, and it uses prime factorizations. So take the two numbers that we're trying to find the GCD of, 36 and 48. Break them down using factor trees. So for example, 36 is 6 times 6, and each of these can be broken down into 2 times 3, all of which are prime numbers down here. So that means 36 is 2 squared times 3 squared. That's my prime factorization for 36. Okay, then I'm going to do the same thing with 48. How can we break down a 48? Several ways of doing that. 4 times 12 is one way. 4 is 2 times 2, and both of those are prime numbers. 12 is 3 times 4. 3 is prime, but 4 is not. 4 breaks down to 2 times 2. So I have 1, 2, 3, 4 2's there. 48 is equal to 2 to the 4th power times 3. 3 to the 1st power, or I can just write that as a 3. Okay, the point of doing this is because one way of finding a greatest common factor between two or more numbers is to just focus on the prime factors and build the GCD from that. So for example, notice both of these numbers have factors of 2 in them. This one has 2 factors of 2, 2 squared. This one has 4 factors of 2, 2 to the 4th. But they both have at least 2 factors of 2. So my GCD, my greatest common divisor of 36 and 48, has to have a 2 squared in it. Notice I'm finding the factors that they have in common, the prime factors, and using whichever one has the smallest exponent, because that means that both of them have at least 2 of those factors of 2. Now, I notice they both have factors of 3. This one has an exponent of 1, even though we're not writing it. This one has an exponent of 2. So they both have at least one factor of 3. I'm going to use that one factor of 3. 2 squared times 3 is 12. That's the GCD of these two numbers. And it's always a good idea to check, is 12 actually a factor of those two numbers? Yes. 12 times 3 is 36, so that means 12 is a factor of 36. 12 times 4 is 48. 12 is definitely a factor of 48. So that is correct. One thing that is worth mentioning here also, that you don't need, I don't think your book talks about this little fact, but it is a useful fact. The greatest common divisor of two numbers will always be a factor of the difference of those two numbers. It's a useful fact that you can use in a number of cases. So when I say the difference between these two numbers, what is the difference between 48 and 36? 48 minus 36. This is like a side note. We've already answered the problem, or answered the question. This is just another thing that would be worth mentioning. 48 minus 36 is equal to 12. If I take the difference between those two numbers, a fact from number theory states that the GCD of these two numbers is a factor of 12. And since we're looking for the greatest common factor, I would look at all of the factors of 12, starting with the largest, and then see if it's also a factor of 36 and 48. Well, remember, the largest factor of any number is itself. So 12 is a factor of 12, and it's also a factor of 36 and a factor of 48. So it would have to be the GCD. I'm not really going to mention that property again. It's just another way of looking at GCDs. All right, I want to do the GCD of three numbers over here. That means I need three prime factorizations: 8, 20, and 44. So 8 breaks down to 2 times 4. 4 breaks down to 2 times 2. So 8 is equal to 2 cubed. 20, what is 20 equal to? Well, I know that it's equal to 4 times 5. 5 is prime. 4 is equal to 2 times 2. So I get 20 equals 2 squared times 5. Okay, what about 44? 44 is equal to 11 times 4. 11 is prime. 4 is equal to 2 times 2. So 44 is equal to 2 squared times 11. Now again, my GCD of these three numbers, my greatest common divisor or greatest common factor, when using their prime factorizations, I'm looking for what primes they have in common. And the only prime number that all three of these have in common as a factor is the number 2. So that's the only prime number that will show up in my GCD. Then I look and see at least how many 2's can I say are in the prime factorization of each one. Well, I have a 2 squared here, a 2 squared here, and a 2 cubed here. The smallest exponent that I see is this 2. That means each of these prime factorizations has at least 2 factors of 2 in them. So I can include that, 2 squared, which equals 4. Okay? And it's easy to verify that 4 is in fact a factor of all three of these. In fact, 4 showed up in all of my factor trees, which verifies that. Okay? So that would be the GCD of those three numbers. A little term here, and this is a very useful term in number theory, relatively prime. So if you have two natural numbers, A and B, if the GCD of those two natural numbers is 1, then we say that those two numbers are relatively prime. Some books will use the term coprime. You have to be careful with this definition. Relatively prime absolutely does not mean that either of these numbers are prime numbers by themselves. They can be, but that's not what this means. You can have two composite numbers, A and B, that are relatively prime. It's describing a relationship between two numbers, not a property of a single number. So, move on to an example. I'd like to show that 45 and 16 are relatively prime. Neither of these numbers are prime numbers. 45 is equal to 9 times 5. 16 is equal to 8 times 2. They're both composite. But as a pair of numbers, they are relatively prime. And we want to show that by finding their GCD. So I can find the GCD the same way that I did in those previous examples. Use a factor tree, 45 and 16. 45, like we said, is 9 times 5. 5 is prime. 9 is equal to 3 times 3, and 3 is prime. So I got 45 equals 3 squared times 5. What about 16? Different ways to break down 16. I could make it 4 times 4. Each of those 4s breaks down to a 2 times 2. 16 is equal to 2 to the 4th. Now notice here that neither of these prime factorizations have any prime factors in common. Only 3 and 5 are prime factors of 45, and only 2 is a prime factor of 16. So that means if I'm trying to build the GCD of these two numbers, 45 and 16, I don't just say that it's nothing. It's not 0. 0 is not a divisor of any of these numbers. But I definitely should not have any prime numbers showing up here, because that would imply that we have prime numbers in common. Well, if I can't find any prime numbers, at the very least, I can always say that 1 is a common divisor of two numbers, because 1 is a divisor of everything, right? 1 always shows up in our list of factors of 45 and 16. So we know at the very least 1 will be a factor in common. If there are any numbers larger than 1 that are common divisors of these two numbers, then I would have had common primes in these two prime factorizations here, which I do not have. So this is what's showing that those two numbers are relatively prime, because their GCD equals 1. Okay? All right, so far what we've done is we've talked about one method of finding the GCF, or the GCD, of two numbers using factor trees and prime factorizations. And it's a very useful technique. But another technique exists that's used a lot in number theory, and it's something that we call the Euclidean algorithm. And we're not going to talk about why this algorithm works. It's kind of an interesting one to ponder over. You might be able to kind of figure it out if you think about it. But we are more interested in knowing, how to use it. So the idea of the Euclidean algorithm, if we're trying to find the GCD of two numbers, and let's assume that one number is larger than the other. If that's not the case, then the two numbers would have to be equal, and the GCD would just be that number. So there's nothing interesting there. Let's just assume that A is the larger of these two numbers. What the Euclidean algorithm does is it divides A by B. So it divides the larger number by the smaller number. And then what it does is it takes the remainder of that result and it divides that into B. Okay, so we take B, divide that by the remainder that we just got. So we're creating another division problem. Then the previous divisor of that last problem is divided by the new remainder, and we kind of just keep repeating this process until we end up with a remainder of 0. Once that happens, we go back to whatever the previous non-zero remainder was. That will end up being the GCD. It's very difficult to keep track of all those steps explaining it this way, so we needed to see an example. We're going to use the Euclidean algorithm to evaluate the greatest common divisor of 288 and 180. And the very first thing we do is we divide the larger number by the smaller number. So I'm going to divide 288 by 180. Okay? And so 180 goes into 288 only once. 2 times 180 is 360. That's too big. So we're going to get a 1, and then I subtract. Okay? And if I subtract this, I'm going to get 108. So that's my remainder, 108. Okay? Now the Euclidean algorithm says take your old divisor and make it the new dividend. So 180 is the thing I'm dividing into, and my remainder becomes my new divisor, 108. Okay? So now, how many times does 108 go into 180? Well, it also only goes in once, and that puts a 108 down here. If I subtract, I get a remainder of 72. Okay? So now, 72 becomes my new divisor. 108 becomes my new dividend. 72 goes into 108 how many times? Okay, well 2 times 72 is 144, which is too big. So once again, it only goes in once. By the way, even though I keep getting a quotient of 1 here, that's not going to happen in every example. That's kind of just coincidental to this one. So I don't want you to get the idea that this should always be a 1. That's not necessarily the case. Okay, we want to subtract this. That gives me 36. All right, 36 is my new divisor. 72 is my new dividend. So now I ran out of space down here. I'll come over to this side. I'm doing 72 divided by 36. Well, 36 goes into 72 exactly 2 times, because 2 times 36 is 72. And notice I got a remainder of 0 this time. That's my indication that it's time to stop. Now that I've gotten that, I return to the previous remainder, which was 36. That number is going to be my GCD for these two numbers. So GCD of 288 and 180 is equal to 36. Okay? That's what we call the Euclidean algorithm. And like I said, we're not going to talk about why this works the way that it does. It'd be an interesting discussion, but I'm more interested in just you knowing how to do it. It is used a whole lot in a course on number theory. All right, so we've talked a lot about greatest common factors and just the concept of factors in general. Now we're moving on to multiples and the least common multiple. So a multiple of a natural number a is any number of the form ak, where k is just an integer. So I like to think of multiples as the numbers that you get by counting by a particular number. For example, some multiples of 4 are 4, 8, 12, 16, 20. Notice 4 is equal to 4 times 1. 8 is equal to 4 times 2. 12 is equal to 4 times 3. All of these can be obtained by multiplying 4 by some integer. 0, even though I didn't include it in that list, is a multiple of 4 as well, because 0 is equal to 4 times 0. In fact, 0 is a multiple of every number for a similar reason. Now, what is a least common multiple? Well, again, kind of like the GCD, we can talk about the least common multiple, or LCM, of 2 or more numbers. And what we mean by LCM, or least common multiple, is the smallest multiple of these two. Let me say it a little bit differently. It's the smallest natural number that's a multiple of both A and B simultaneously. Okay, so kind of the most direct way to evaluate the least common multiple of two numbers, like this example down here, LCM of 9 and 12, is to actually just list out, multiples of those two numbers. Now, there's an infinite number of multiples of any number, right? Because this ... here indicates that I can keep counting by 4s and never really stop, and then I have a whole list there, all of multiples of 4. So you can't write out an entire list of multiples. That's impossible. What you can do is list some, and then see if you end up with something that both lists have in common, counting by 12s. 12, 24, 36, 48, 60, 72, ... Notice that both lists of numbers have a 36 in common. And that is also the smallest number that both of these lists of numbers have in common. That is going to be my LCM. LCM of 9 and 12 is equal to 36, because it's the smallest multiple of both 9 and 12 simultaneously. Now, something interesting about LCMs, the least common multiple is not the only common multiple. Notice when I was counting by 12s here, I got to 72. If I kept counting by 9s, in a couple more steps, I would have gotten to another 72 over here. So 72 is also a common multiple of 9 and 12. In fact, if you notice, 72 is 2 times 36. 72 is a multiple of the LCM that I found. And in fact, it turns out that every common multiple of 9 and 12 will be a multiple of that LCM. Let me circle that. Now, we used prime factorizations as a means of finding GCDs or GCFs of two numbers previously, and we can actually use a similar concept for LCMs as well. So in this example, I'd like to find the LCM, the least common multiple of 24 and 60. I'm going to create factor trees for each one of these to find prime factorizations. 24, for example, is 4 times 6. 4 is 2 times 2. 6 is 2 times 3. All of those are prime. So 24 is equal to 2 cubed times 3. What about 60? 60 is equal to 6 times 10. 6 is 2 times 3, and 10 is 2 times 5. All of those are prime. So that 60 equals 2 squared times 3 times 5. Now, if I were looking for the GCD of these two numbers, I would be looking for what factors they have in common. And then I'd be using whichever one gives me the smallest exponent. That was sort of our technique that we used. LCMs are the other direction. I'm not just interested, I'm not really interested in what they have in common. I just want to build a number that contains all of the factors of both of these. So for example, LCM of 24 and 60. I notice that a prime factor of 2 shows up. And I have 2 cubed here and 2 squared here. I'm going to use the 2 cubed because that way my LCM, when I compare it to each of these numbers individually, it has enough factors to account for that, and it has enough factors to account for that. We're not adding these exponents. I'm not saying there's 3 2's here and 2 2's here, therefore I need 5 2's here. I'm using the largest exponent. Okay? Next up, I notice that I have some 3's. And I have the same number of 3's here as I do here. I have 1 here and 1 here. So my LCM is going to include that single 3. Now, I also notice that a prime factor of 5 shows up. Even though there's no prime factor of 5 over here, I still need to use it because it shows up somewhere. There's only one 5 showing up in the whole thing, so I'm just going to use that 5. Okay? Now we can multiply this out. So 2 cubed is 8 times 5, that would be 40, times 3, that would be 120. 120 is the least common multiple. Okay, now can you verify that using this other technique? Sure. You know, you can count by 24s and count by 60s. 60, you know, you'll get to 120 counting by 60 counting by 60 twice. 60, 120, 180. That would be the second number that shows up. 24, you only need to count by 24 5 times until you get to 120. So this is definitely a common multiple. One thing that's worth mentioning, if you find the least common multiple or any common multiple, this number should have both of the original numbers as factors. That's the relationship between multiples and factors, or multiples and divisors. Let's use another example where we have 3 numbers. I'd like to find the LCM of 8, 20, and 30 using a similar technique. So 4 times 2 is 8, and 2 times 2 is 4. We've seen this one already in a previous example. 8 equals 2 cubed. What about 20? 20 is 4 times 5. 5 is prime. 4 is 2 times 2. So I can write 20 as 2 squared times 5. And then finally 30. 30 you can break down a lot of different ways. 3 times 10, for example. 3 is prime. 10 is 2 times 5. That means 30 can be written as 2 times 3 times 5. Same idea as before. So if I want to build my LCM out of these prime numbers, 8, 20, and 30, I notice that a 2 shows up in at least one of my prime factorizations. It turns out to show up everywhere, but it really just needs to show up somewhere in order to know that I need to use it. The most 2's show up in this prime factorization, 2 cubed. That means there's 3 2's showing up in this, and I go with the largest exponent, 2 cubed. I also notice that there's a factor of 3 showing up somewhere, and even though it only shows up in this prime factorization, I have to use it, so that gives me a times 3 here. Finally, I have a couple of 5s showing up. And the most 5s that show up in any prime factorization out of all of these 3 is just 1. Each of these only has a single 5. So that's times 5. Interestingly enough, this is coincidental. I also end up with 120 here. Okay, that's coincidental because of the numbers that I chose. But you can verify 8, 20, and 30 are all factors of 120. That means 120 would have shown up in all 3 lists of multiples. Okay, a little bit left to do, and then we will be done here. Wrap this up in one video, I think. We're not going to prove this formula here, but you can do it using what we've been doing with prime factorizations. This is actually a consequence of how we've been dealing with GCFs and LCMs using their prime factorizations. Although the formula itself, when we use it, doesn't require us to do any factor trees or anything. Basically what this says is that the LCM and GCF of any 2 natural numbers, A and B, have a relationship to each other. The LCM of 2 natural numbers is always equal to whatever you would have gotten by just multiplying the 2 natural numbers as they were, then dividing that product by the GCD of those 2 numbers. Okay, so this establishes a relationship between LCM and GCD. Let's look for a place to use that. Here I want to find the LCM of 36 and 48. I can do that using the prime factorization technique. It's not difficult. However, I want to try using this formula. Now, we have already found the GCD of 36 and 48. That was one of the first examples we did at the beginning of this video. We found that it was equal to 12. Okay, so I need to use that because this shows up in my formula. According to that formula, the least common multiple of 36 and 48 is equal to the product of those 2 numbers, 36 times 48, divided by the GCD of those 2 numbers, which was 12. Now, I would advise against doing 36 times 48 first and then dividing by 12, because 36 times 48 is a pretty large number, and then dividing that by 12 is, not the worst thing in the world, but it's a long division problem. Granted, if you had a calculator, that's no big deal, but I'd like to try doing this without a calculator. Notice that 36 and 48 are both divisible by 12. That should come as no surprise, because remember, 12 is the least common or the greatest common factor of these 2, which means it is a factor of each of those. That means I can cancel 12 with either one of these. So, for example, if I divided 12, or if I divided 48 by 12 and 12 by 12, this becomes a 1. 48 becomes 4. Okay, this is equal to 36 times 4, which equals 144. It's an easier way to do that. Notice that formula, using something I had already found previously, was actually much faster than finding a big factor tree in a prime factorization. So there you go. All right, last thing that we want to look at to wrap things up is a word problem where the concept of LCM comes into play. So let's read this first. I think this is Yomas. And Yomas and Raquel work as security guards at a factory. Yomas has every 6th night off, and Raquel has every 10th night off. If both are off on July 1st, what is the next night that both will be off together? So think about it this way. Let's ignore the July 1st for a second. If I look at, just days on which Yomas is off, he's off every 6th night. So once he's had a day off, he has to wait 6 more days before he gets his next night off. And then he has to wait 6 more days, which would be 12 days from that starting point. And then he has to wait 6 more days, 18, and then 6 more days, and then 6 more days. You can kind of see how he has this waiting period of 6 days between each day off. Okay? Now, Raquel has something similar. Raquel is off every 10th night. So if she gets a particular night off, she has to wait 10 days until her next day off, and then 20 days from that starting point until her second night off, 30 days, and so on. We're counting by tens here, right? What are we looking for? Well, if both Thomas and Raquel have July 1st off, and we're asked to find the time or the day at which the next day that they're both going to have off, Yomas will have a day off before Raquel. He only has to wait 6 days while she waits 10. But because these are offset, eventually we will have a day where they sync up again. And notice from a particular day, Yomas and Raquel, if they both wait 30 days, they'll have another night off together, because that's a multiple of the number of nights that they have to wait that shows up in both of their lists, the least common multiple, in fact. So the very next day that Yomas and Raquel are going to have off after July 1st would be 30 days after July 1st. 30 days after July 1st would be July 31st. Okay? So you can see where least common multiples kind of plays into a word problem like this. That's going to wrap up 5.4.